So when it comes to dynamic loading, to have a cost-effective design, if you consider a very heavy vehicle on all the lanes, then the bridge will be extensively big, the beams will be extensively deep, and it will not be cost-effective, right? So when you talk about combination of loads for bridges, you have the principal combination and you have the secondary combination. So you have load combination 1, 2, 3, 4, and 5. So you need to check for all these load combinations and see generally to see which one will have the worst effect. Okay. If you look at load combination 1, you have permanent loads plus live loads. Okay. Permanent loads, what are these permanent loads? Permanent loads is basically the self-weight of the structure and also the permanent fittings on the structure, like your bridge parapet rails, your concrete curb, okay, your deck slab, the beams. So all these are permanent loads, right? Live loads, we will look into it as well, all right? Live load, generally you have the HA loading and HB loading. Later I will explain what is HA and HB. Apart from live loads, for bridges which is on a high terrain, you need to also design it for wind loads. Bridges only at high terrain, not the lower level ones. And at many instances, there have been cases where they have missed out temporary erection loads. If you come across during construction work, where you have a situation at site, there is a collapse or, there is some mishaps and accident, that is normally due to temporary erection loads. Sometimes engineers, they focus too much on the loadings required by the BS code, but they forget, they may miss out the temporary erection loads. Okay, temporary erection loads is not written. I mean, it is just written generally in BS 5400, but then it is not elaborated extensively because you need to look at it as per the characteristics of the construction itself. It will differ from case to case. So the engineer has to study and consider temporary erection loads as well. Okay. Load combination 3, you have permanent, live load, temperature range and difference. Temperature range and difference, I think for Malaysia is not so much because ours is like 20 degrees and up to 40 degrees. But in other countries, it can be from 0, -5, up to 40 degrees in summer. So that one, you look at the temperature range and difference, basically to design your bridge joints and so on. Load combination 4, you have permanent loads, you have secondary live loads, okay, and you have some live loads. It is basically a combination of live loads. Secondary live loads is loads like knife edge load. We will look into it later. What is secondary live loads? Primary live loads is your HA, HB. And load combination 5, you have permanent loads and loads due to friction at bearings. This one also we'll look at it later. Okay, so loads due to friction of bearings is for you to design the bearings itself. So the function of the bearings is to transfer the force from the superstructure to the substructure. Okay. Now, what is permanent loads? Dead loads, superimposed dead loads. So dead load is normally noted as DL. Superimposed dead loads is noted as SDL. And loads from creep. So dead loads is the weight of the structure itself. Your superimposed dead load is like your asphalt layer, your parapet railing. This is superimposed dead load. That means you are imposing something on top of the primary dead load. So the primary dead load is actually your beam, your deck slab. Superimposed dead load is like the asphalt, your parapet railing, and so on. Transient load means loads which can move. All right. So transient means it can move. So primary life load, you have HA and HB. Right. HA loads are called as normal loading. HA means normal. HB is abnormal loads. All right. So for bridges, you have HA and HB. Secondary loads, which is not as big in magnitude as HB, is braking, skidding, and collision. Collision is normally towards the parapet. Okay, so braking also can be calculated, but this braking and skidding, basically, if you have already considered enough of HB, HA, and HB, when you check for braking and skidding, it will pass because the magnitude for braking and skidding is not much. But for collision, it applies for parapet. Normal parapets are designed for 50 kilonewton. We'll look at it later as well. Okay, now HA is actually normal loads. You have three types of HA. You have uniform distributed load. All right. You have the knife edge load. Knife edge is actually something like the load from the wheel. You have a tire and so on. So that particular tire or your wheel, the lorry's wheel, will give an effect just like knife. So the knife will move on any part of the bridge. So the knife edge load is a fixed value. It's 120 kilonewton per notional lane. What is notional lane? Notional lane is defined with a certain width. You can have lanes 3.65, you can have lanes 4.2, you can have lanes 4.1, all different kind of lane widths. So the notional lane has been defined in PS. Okay, notional lane means like 3.5. All right, so this is notional lane. This is for analysis. And you have wheel load. Wheel load is 100 kilonewton with contact pressure dispersed through asphalt. Okay, wheel load means the weight transmitted to the road through a wheel and its tire. Okay? So it doesn't differ much from the knife edge load. So we can just consider the knife edge load. All right, now HB is the abnormal load. Abnormal load, like for highways, I think like Pan Borneo and Plus Highway and all, most bridges have been designed for HB 45 units. Okay, HB 30 units mostly used for housing areas and rural areas and so on. HB 30 units. Okay, and what is the meaning of HB 30 and HB 45? So 1 unit is 10 kilonewton. Okay, one ton is 1,000 kg, which is 10,000 newton. So 1 ton is actually 10 kilonewton. All right. So 45 units means 45 tons per axle. 45 tons per axle. So you have how many axles here? 1, 2, 3, and 4. So 45 times 4 is 180 tons. So if somebody asks you a question, like, you have like Penang Bridge, okay, Rosidi, you have Penang Bridge. So somebody asks you a question, what is the maximum weight of vehicle allowed on the Penang Bridge? So Penang Bridge have been designed for HB 45. So the answer is 180 ton. Okay. So you can't allow a vehicle which is more than 180 ton to be used on the bridge. All right. Any questions so far? So we move on. So this has to be clear. Like if HB 30 is a 30 ton, so 30 times 4 axle, 120 ton. Okay. So sometimes the bridges in rural area and Taman and so on, we just design it for HB 30. We don't use it for HB 45 because there are no commercial uh, industrial connections around the area. This is a chart which I just inserted. This shows how is normally the span is analyzed for different loading. Okay. Now, it would not be economical to impose HB on all the lanes because the chances of having a HB vehicle on all the lanes is almost uh, nil. So what they have done, this HB vehicle is very heavy. So what they have done, they have only considered HB vehicle on one lane, or it can straddle between two lanes. You know, it can be in the middle of these two lanes. You know, so whenever you consider an HB vehicle, you must allow no loading for 25 meter and 25 meter in the front and the rear. There should not be any loading. At the back of it, you can have your full HA and full HA. So for in terms of an economic design, on the other lanes, you can consider 1/3 of the HA because the HA itself is already conservative enough. So you just need to consider 1/3 of HA for other lanes, you know. So as long as you use a diagram similar to this to load it into your structure analysis, then the design of the beams should cater for your HB vehicle. You just change the HB vehicle loading for the type of HB vehicle you want to allow. So you definitely cannot allow HB in all the lanes. And even then, the most economical type is you allow HB in one lane and the lane beside it allow for full HA, or you straddle. This HB will be on two lanes, you know, straddling between these two lanes. And your lane number 3, you allow for 1/3 HA, and all the other lanes you just allow for 1/3 HA. You have already complied as per the BS standard, and the bridge design will be safe. Okay, this is how you do the design. This is a basic thing. Okay. Apart from this, these loadings can be worked out by manual calculation or by computerized calculation, and just assume the span is simply supported to get a higher bending moment, and your design will be conservative and safe. Okay. Apart from the HA and HB loadings, the other loads which you can consider is centrifugal load. Centrifugal load are the loads which arise when the bridge curves, you know, when the bridge curves, especially when there is a horizontal curve, then you will have a centrifugal load, which is when the vehicle moves on top of it, is trying to push the beams outside. So that you have to consider. But this is only for lateral stability lah. So as long as the bridge does not curve, whatever loads we have said in the previous slide is already good enough. But even if the bridge curves, and normally unless the curve is very significant, then there is an effect. If not, means there will not be much any changes to your beam dimension and so on. Okay. Number 2 is for skidding. You need to check it for skidding. But basically, if you've already considered HA, HB good enough, like what I've said just now, it should be okay. Collision of parapet is different. This you got to analyze it separately, right? Depending on what parapets you want to use, which we'll see later on as well. Now we go to type of bridges. Remember, these bridges have been around for a very long time. So some people ask me, even in those days, they have bridges, right? So bridges hundreds of years old also can last. Whereas the new bridges, some of it has got problem, right? So the simple answer is that the old bridges have been generally designed as a arch bridge. Okay, the span length is very short, only about say about 4 to 8 meters each span. So it's done by masonry, by bricks and cement and stone and so on. And you can have your brick arrangement, but it's very important. If you can see my cursor here, it's very important for these few bricks around here. Now these bricks must be wedged inside. If these bricks were to detach, then you will have a stability problem, and it can also collapse. Okay. So the arch bridge is always under compression. There is no tension. If you see how my arrows is acting, it's always under compression. There is no bending action here. And short span and mostly ancient bridges. All right. So what is very important for the arch bridge is that during construction, extreme care must be taken on how to lock the wedges inside. The wedge bricks is actually bricks, but has to be fitted in tightly so that it does not detach. Examples of the arch bridge, you can see, all right. So which is the important, very important member here is the brick which is on top around this area. Can you all see my cursor? Hello?
Yes, yes.
Can, okay, all right. I'm waiting for answer. Okay, so you can see that. Okay, so that is a very important area of the arch bridge, right? Short spans. You can see this is a very short span. This is another modern arch bridge. Okay, it's made of a steel frame. Right? This one has got bending action. So the bending action have been tied similar to bow, So it's similar to a bow tie bridge. All right. So this gives much more height clearance we need for ships to pass under. Okay. The largest span tension is present. Well, in this one, there is no tension. Everything is under compression. Okay. Span only about 4 to 5 meter. And here you have tension. This member will be under tension. Other arch bridges, okay, so some of the bridges have been designed, have been built more than 2,000 years ago. Okay, so bridges have been designed, have been built thousands of years ago, but the concept is under compression. Okay. Now, suspension bridge. What's the meaning of suspension bridge? Suspension bridge is the bridge is suspended in the air, right? So suspended in movable cables as well. Like here, you have a simple suspension bridge. You tie it to some trees. Okay, so this is also a suspension bridge. Examples for suspension bridge is the Clifton Bridge and the Humber Bridge. Okay. Cable stayed bridge is also a type of suspension bridge. Okay, and the concept is that the cables are not movable, is stiff. But again, you have two types of cables. You have the unbonded tendon and you have the bonded tendon, right? From what I understand, those cables for some bridges in Sarawak are coming under the coastal road are stay cables with unbonded tendon. That means when you have stiff cables, like the one in LDP Sunway, inside the cables, you have concrete filling. So the cable is stiff. But another type of design is also like Penang Bridge, where inside the cables, you do not have concrete fillings. So the cable can actually sway. Yeah, cable can actually sway. There are advantages and disadvantages of that. So generally, these very stiff cables are used for stay cables which are not as high as 40 meters and above. Say only about 10 meters or 15 meters, then you can use stiff cables. Okay, because as the pylon goes up, and the height of the cables increase, there will be wind action on top of it, wind and rain. So if you have stiff, then you need to do the analysis for stiffness. So your material inside that has to provide that. So and the other reason is that when you have unbonded cables, you have room for replacing each strands in the future. Whereas if you have already concreted those cables, you can't replace any of the strands. Examples of stay cable bridges. Okay. Strong steel cables are stretched between support and deck. Okay. Although there are many stay cable bridges, it's good that Sarawak is going to have about 4 or 5 major stay cable bridges. It's a small stay cable bridge. We have one, of course, the shape is different. In Putrajaya BR8, it looks more like a violin shape. And here we have our well famous Penang Bridge. Okay. As you can see, Penang Bridge, the cables are at a height, and the height of this pylon is easily about 60 meters on top, 60 meter. So these cables are flexible in the sense that inside the ducts, you have the tendon and there is no concrete or grout filling inside. So actually, when you have high wind and rain combined together, the cable can also vibrate. So beam bridges is a sketch of a common modern bridge. You have beam, you have abutment, and you have pier. Types of beam, all right? You have N beam, you have U beam, you have inverted T, and you have I beam. Okay, N beam is given the name N because of the shape on top, like M like that. Okay, you have U, inverted T, you put up the T in an inverse way. That means what they call it, T yang terbalik, and you have an I beam where the shape of the cross section is an I. Right? This is common type of beams found in bridges. So girder is a structural member which used for crossing application. Okay, so we look at what is girder about. Precast segmental girders normally are launched by launching girder. In example, the LRT project. Okay, and you have two types of box girders. You also have casting the segments. You also have cast in situ segmental girders, where you cast the segment at the side. Okay. So, and you have your precast segments where you cast it at the factory and you transport it to the site, which is much easier to be done. Right? So LRT, most of it, they were using precast segmental girders. So when do we use beam or box girder? Okay. Remember this, for beams, the maximum span length is about 60. Only then you get your proper L over D ratio. So for generally, for ease of understanding, it's very difficult to design a beam for more than 60 meter for bridges. Okay. If you go beyond 60, then your depth will become very deep. Okay. And so normally for beam, it's below 60 meter. Generally, is the very common length is 40 meter. So for larger span length, what do you do when you need a crossing which is more than 60 meter? So you design a box girder. Why they call it box? Because inside there is a void. So it's like a shoe box, you know. So it's a box because inside there is a void. Okay, so you can have recessing cables to it to give it more uplift effect. Okay, when you design for pre-stress, you need to use a method called load balancing method. So when you tension these cables, the box girder will have a tendency to lift up. Okay, that means to hog. We call it as hogging. Okay, we have hogging moment and we have sagging moment. So when you stress the cables, the segment will try to hog up. Of course, you can't see it in your naked eyes. You need a theodolite to check it. So it will tend to hog up. So once your load comes in, it will become deflection zero. All right. So that is how you you decide whether you want to have beam or you want to have box girder. Okay. So how to determine the best type of bridge to suit your requirement? Okay. Now case one, you need to cross a stream. So how do you do that? Anybody can answer me on this? Do you go inside and swim?
Jump
Huh?
across.
You jump across. Okay. Anyway, that's one of the way as well. What you can do is you can just put up a wood and it will act like a beam.
Bridge.
Okay?
Yeah.
Actually, the wood or the tree trunk itself can now be called as a girder. Am I right?
Good.
Yeah. Girder doesn't mean it has to be a concrete beam. So in this case, what is a girder? The girder is a tree trunk. The tree trunk has become a girder. What is the meaning of girder? Just an element which we use to cross.
Oh. Gitu sebenarnya.
Tak, itu sorry. So yang ni pun kita boleh panggil dia sebagai girder sebenarnya. So kalau kita ada kurang daripada 50 meter, we have river. So what's the best way? You can't drive the car inside. You got to do a beam. Am I right? Unless like a James Bond car lah. So you got to do a beam. So now you have a beam girder. Okay. So the tree trunk was also a girder. So case 3, Malaysia, Singapore, beam bridge is not possible. So we use box girder. Okay. Now we go to bridge terminology. All right, this is the general bridge terminology. So you have abutment foundation. Abutment foundation is under substructure. I forgot to write the substructure here. Okay, abutment foundation, and if there are piers, supposing there is a pier here, then the pier is also under substructure. Okay, remember that. Superstructure is on top of the bearings. The bearings is a connecting element between superstructure and substructure. All right. So they are divided into two parts. For bridge, substructure are the elements which involves the which are connected to the foundation, the piles. Okay. So we have a pier here, the pier column is a substructure. The bulkhead is a substructure. So the bearing connects the superstructure and the substructure. Okay, you have the approach road, a retaining wall, and so on. Okay. This is the numbering convention. So you have your span, and normally the direction to the north or east will take the precedence. Okay, keutamaan diberi kepada arah ke timur ataupun utara. So we start our naming from north or east. Okay, this is a south bridge. So we start our naming from north or east side. So the first bridge joint towards the north side is known as joint number 1, joint number 2, joint number 3. And then you have a span 1, span 2, span 3. You look here that when the first joint is named based on the direction towards north or east. So in correspondence, the adjacent joint at the other bound will also become joint number 1. Right? Abutment A is either the north abutment or the east abutment. Abutment B is either the south abutment or the west abutment. This is how the abutment is. Okay, this abutment, is it a substructure or superstructure? Anyone can answer me on that?
Substructure.
Yeah, abutment is a substructure. Why is it a substructure? Because it is connected to members which are directly connected to the piles or whatever foundation they have. Okay, this is embankment, and you have a ballast wall. We can also call it as abutment wall. Normally we call it as abutment wall. This is a wing wall. Okay, wing because it looks like a wing, so it's called a wing wall. Normally the function of the wing wall is to retain the earth field at the abutment. Okay, and your bearing shaft, and this is abutment wall. Okay. Now, this is how the arrangement of the superstructure and the substructure is, and the connection will be here with the bearings. So what is the function of bearings? Bearings is a member which connects two different structures. Okay, so in this case, your bridge has got two different structure. One is superstructure, and the other one is substructure. This is how the type of beams and the deck slab. Deck slab and precast beam, I-beam. So another picture of precast beam is not common. This kind of precast beam is not common. You have beam, road, and deck slab. Okay. So superimposed dead load, SDL, is the road material and your parapets and your curb. This is SDL. All right. Your dead load is the beams and your deck slab. your live load is the crater and all on top. Okay. Again, we show the beams. Okay. This superstructure, you have different kind of piers. So this is the wall type of pier. All right. You also have other type like hammer type and so on. This is a column type of pier. Penang Bridge has got this column type. The Shah Alam Bridge at kilometer 0.9, where our Encik Effendi was involved last time when we was here. So that is a wall type. Penang Bridge is column type. This is a frame type. You have two columns, right? So you have generally you have these three types lah. Okay. Sometimes we also have another type. It's called the hammer type, macam penukul. Okay. That one I did not draw it here, but we do have another hammer type, which can have only two columns, and we also call it as a hammer type. Now the bridge joints is this is the diagram of the normal asphaltic plug joint. Okay. 500 mm is nominal. How is it designed? Is because when you have two structures at the connecting span, due to its thermal expansion and contraction, so your asphaltic concrete, if it does not have a joint, then the asphaltic concrete will crack. So we must introduce something which is flexible on top of the joint gap. So what we can have is we can have mechanical, or we can also have rubberized bitumen. So it's flexible. Asphaltic concrete is not as flexible as rubberized bitumen. Rubberized bitumen, you can basically pull it. Okay, it will have some elongation values. This is a buried joint. Sometimes when you drive, you do not feel any joints on top. So what they did was they have constructed a sliding plate and steel angles, so that but buried joints can only be done for gaps like 30 mm and below. You can't do this for larger gaps. Okay, so this sliding plate is allowed to move, and on top of it you can have your roadwork material. Okay, so you will not see a buried joint from the deck. You'll only know there's a joint by looking from the side or under a bridge, right? This is a mechanical joint. It's a nosing type. So you have a rubber in the center, and you have some steel angles and steel members casted into. So these joints can be chosen for more larger gaps, which is 50 mm or 60 mm or 80 mm. So you can adjust, or you can buy a more bigger rubber to be slotted in. Okay, so it is also a very good waterproof joint, where due to the rubber in compression, so you can minimize or stop any drainage of water from the road and to the pier below. If not, it will look you'll have water stains. So this is a very good joint, but normally it can only be done during construction stage, because you have a few steel members which has to be concreted into the deck slab. Very difficult to do this after construction, because you would need more road closure times and for the concrete to actually set. But these joints are done at the beginning of the construction, and generally it can last very long. Easily 10 years it can last, no problem. This is a buried joint with sealant. We saw the buried joint just now. Just to counter any probability of the pavement cracking, so we can cut the pavement a little bit and just add on some sealant inside. So when you remove this joint, you will not see a gap down. You will not see a gap. You can see a steel plate, or you can just see the concrete deck itself. So this is a sealant joint. We call it sealant joint. So it's actually a buried joint with sealant. You may not find any gap below. The idea of putting up a sealant is, if in case this pavement is trying to crack, it will crack on along the sealant. It will not crack on the sides. Okay. Now this is the example of elastomeric bearing. I choose this photograph just to show that some very old bridges and bridges where you have water seepage problem, water seeping from the bridge joints. This is how bad the bearings can be. Okay, and you have bearing pad and you have laminated bearing. Laminated bearing, it consists of a rubber matrix with steel plates inside the rubber. Okay, rubber alone may not have, will not have the enough compression and also bridging strength for its function.
Pubalan,
Yeah,
sorry, interrupt.
it's okay, no problem. Can talk. I mean, this session is open. Please free to ask questions.
The elastomeric bearing, this one for fixed side, isn't it?
It's for movable side and also for fixed side. You see, the function of the bearing is to connect between two members. So supposing this one is a fixed side, even though it cannot move, even though this beam cannot expand and contract due to thermal at this area. When you say fixed, you'll have a dowel inside here. Of course, you can't see the dowel, but you still need one member to connect the beam and the pier.
There must be a pair lah, because on the other side will be mechanical pot bearing lah, isn't it?
Not exactly. Depends. You see, for a mechanical pot bearing, you can use it. We will see in the sketch later. I also have got a slide on that. Mechanical pot bearing is when your bridge have got some curvature and there's some slight rotation to it. This laminated bearing cannot take rotation, very little. If your bridge is like curving slightly or your span is bigger, then you have your mechanical bearing that can take more rotation. You see, like bearing, the first function, it has to take the axial load coming from top. All right, but when you have other things, like you have some centrifugal force due to the bridge curving, then laminated bearing may not be appropriate. You have to use the pot bearing.
That's mean usage for this elastomeric bearing. This one just able to cater small tolerance,
Yes, exactly. And for bridges on a straight profile, it has to be fitted at the fixed end and also the free end. At the fixed end, what is its function? Just to connect the beam and the pier. That's it. But at the free end, what's its function? It can also allow for some movement. This is the bridge parapet, NJB, okay, with handrail actually. It's actually with handrail. This is another type of parapet rail. Okay, now we go to the type of bridge parapet design. There are three kinds of bridge parapets you can design. You have the low level of containment, you have the normal level of containment and you have the high level of containment. Okay. Now we see what is low level of containment. Okay, low level of containment. Okay, I think there's a small typo error here. Low level of containment, I know is for a car which is about 800 kg. 800 kg, yeah. So I'll change it later. Angle of impact is 20 degrees. Okay. Normal level of containment. Okay, sorry. The low level can 1500, but speed is 80 km per hour. The normal containment 1500 kg, speed is 113. Height of center of gravity, this one is on the vehicle itself, 600 mm. Okay, this is what they say we use for the analysis. Angle of impact is 20 degrees. So generally this design is used the most. So for most bridges which we see around us, where we have the NJB, the standard NJB, the 1 meter high one. So the level of containment for the parapet is normal containment. And if you have a lorry, which is about 10 ton or 20 ton, traveling 120, so the lorry can crash on the NJB and it can be thrown off the bridge. All right. So the general design for the bridges around our area is for normal containment. So if we see a lorry which has been overthrown out of the normal bridge, that is not the problem of the bridge. It is a problem of the lorry and the driver itself. Okay. We can't design all the bridges for high level of containment because it will not be economical. Okay. Now we look at high level of containment. High level of containment, you design for a vehicle which is 30 ton traveling at 64 km per hour. And the height from the center of gravity, this is generally where the bumper is, the car's or the lorry's bumper, or the lorry's bumper, and generally lah. So it's about 1.65 meter. Angle of impact is 20 degrees. Okay. So high level containment, this design is used the least. It is mainly used for crossing at a high risk area. In example, a heavily populated area, chemical storage and railway lines. So if you travel at areas where there is a railway line below, you can observe the type of parapet, and the parapet rails will be different from the type which you see at other bridges, because the specifications required by railway authorities